Hello and welcome to the second session of our free online workshop, CFD Simulation for AEC application, organized and delivered to you by SimScale in cooperation with Vind-Vind Engineering and McNeel Europe, the makers of Rhinoceros. It's great to see again so many people who have joined for our today's lesson. And for those of you who were with me last week, you will already know the procedure. Before we start to talk about the actual topic, I would like to make sure that everybody can hear me loud and clearly. And we are using a software called GoToWebinar to deliver this live stream of this session. And you should see now on your desktop the GoToWebinar control panel. And there is a button called Raise Your Hand. And please click on this button in the case you can hear me. All right, I already see some hands. Seems like everything is working great. All right. By the way, we also offer an alternative. You can also use our toll-free audio service number to listen to the voice of the presenter. And therefore, you just have to dial one of the toll-free numbers you can see on your screen right now. And once you're asked, please enter the access code 138-574-055. All right, since everything seems to work from a technical point of view, let's take a quick look at our today's agenda. First of all, I would like to take a short look back on our session last week, which was the first session about wind comfort and wind comfort prediction with CFD. And last week, the presentation was basically made out of two parts. So first of all, we discussed some very fundamental concepts of CFD. And in the case you missed the last session, I really recommend to take a look at the recording we sent to you by email. And in the second part of our last week's session, our guest speaker, Per, who will also join today, introduced you to the very basic concepts of wind comfort. We talked about different criteria for wind comfort, how wind comfort can be impacted or optimized with CFD. And finally, we had a live demo where I showed you how to set up a simulation on SimScale and what kind of analysis we can perform later with the results. And today we will focus on another very important aspect of building aerodynamic, which is about wind load. And therefore, at the beginning, we will again talk a little bit about the fundamentals of CFD. We will dive into a little bit more advanced concepts and talk about the main modeling aspects of computational fluid dynamics. Followed by that, Per will introduce you to the fundamental concept of wind load engineering. And again, we will have a live demo where I show you how to set up such a simulation on your own and also how to analyze the results. And at the end, for sure, we will again have time for Q&A. Just because some people seem to have joined this week for the first time, I would like to tell you again that we will record all of these webinars and send you the recording approximately tomorrow. And in the case you have questions during the session, just write them into our question toolbox. And Per and me will try to answer this question directly in the chat or discuss them with you during the Q&A in the case the question is might relevant to a larger audience. All right, so let's get started. And first of all, we will continue our journey through the very fundamentals of CFD. And last week, we basically just talked about the basic concept. So what is CFD? We found out that CFD is basically a kind of virtual wind tunnel which allows you to virtually test and predict the behavior of fluid flow phenomena. And today we will try to understand a little bit more in detail what does it exactly mean and which components are necessary to prepare a successful CFD simulation. So I've prepared the slides, and on the slide right now you can see the 6 most important, let's say, modules or components of a successful CFD simulation. And I'm quite sure if you take a look at other books, maybe they use some different terms. And in the end, there were like hundreds of possibilities how to explain CFD. But this explanation is really tailored to the SimScale platform and also to the rest of our course. So I hope that it will add some value to you and help you to understand how CFD is working. But first things first. So let's start on the very left side. And one component for every CFD simulation we already discussed last week is the mesh. As you remember, during the meshing, we need to discretize our continuous fluid flow domain. And let's take a simple example again. Let's say we want to perform a virtual wind tunnel test of a flying car. And this white shape is representing our car, while the gray shape is representing the domain around the car, which is our virtual wind tunnel cross-section. And when doing CFD, first of all, we need to create the mesh, which means we need to tell the computer where we need which kind of accuracy. And basically what we're doing is we're dividing our fluid domain into a lot of a finite number of simple shapes, in this case hexaeders, and instead of calculating the simulation result for every point of the domain, which would lead into an infinite number of control points, we just calculate the solution and pressure, velocity, and all the other flow quantities only for the center of the cells. And the great thing is that this allows us to adapt the accuracy of our simulation. For example, we will need to refine the mesh there where we expect to have high changes of the flow field. So everywhere we expect to have, for example, very high velocity changes or very rapid pressure drops. And great thing is that when using SimScale, you basically can have the choice. You can use automatic mesh, but you can also have full control over all meshing parameters if you want. And we have several kinds of refinements which you can use and which you should use, because one thing you should keep in mind all the time, the perfect CFD simulation or the perfect mesh is as coarse and small as possible and as, let's say, fine and large as necessary. And besides the edge refinement, you can also refine whole surfaces and even the volume or define areas of your fluid domain. And if you take a look at the slides, this is, by the way, also the way our meshing algorithm for parametric hash meshing is generating the mesh. So we're starting with a background mesh, which you have to specify. So at the beginning for your mesh, you just define like the total size of the fluid domain and the initial mesh size you want. And then you can define individual refinements for, as I mentioned, for edges, for example, or faces. And then these refinements are applied to your mesh. And at a very late stage, the mesh automatically deletes all the inner cells. And then finally, you snap the cells or project them on the surface of your model, and that's how we generate the mesh, by the way. Another very important aspect of meshing is the wall modeling. And I don't want to go too much into details here, because actually wall modeling is a sign on its own. And a friend of mine, for example, is right now writing his PhD and is only focusing on one kind of wall modeling. But let's try to get a rough idea what wall modeling is about. So in the case you ever worked your own on a dynamic project, I'm quite sure you heard about the so-called boundary layer. And the essence of the boundary layer, or the boundary layer theory, is that if we have a fluid flow which is streaming around, let's say, a solid body, we have interaction between the fluid flow, or let's say the air, and the wall. And if you take a look at the flow in the near of the wall, you will notice that this flow has a kind of different structure compared to the outer flow. And the reason is that we, from our experience, most of people think that air or that air streaming around the body has no friction, but basically that's wrong. And it's more like that the nearest layer of air in the near of your surface is directly in touch with this body, which means that your local flow velocity directly on the surface of the surface is zero. And this means you get a kind of profile on velocity profile on your wall, and if you take a look at this, you can see that basically you really have this kind of profile, and that this profile is changing also. And it's very important to understand that what is happening inside this boundary layer is very important for your overall physics, and a lot of, let's say, macroscopic things of the flow topology are controlled by the boundary layer. Why I'm telling you this? Because simulating the boundary layer is really difficult because we have really high changes. If you just take a look at this image on the left side, you can see, like, inside the boundary layer what kind of complex flow structures we have. And especially what is a big problem is to properly model the velocity profile of the boundary layer. Because by definition, the boundary layer is a part of the air where the velocity is lower than 99% of the free slipstream velocity. And this is how wall modeling is connected with meshing, because if you think about it, in the boundary layer, I have a very large gradient in x direction, in y direction. So let me try to sketch it. So in this direction, I have a very high gradient, which means I have a very high rate of change. The velocity is rapidly changing from 0 to free stream velocity. While if I take a look in this direction, the x direction, there is a very small change, a very small gradient. And if you think about it, it means I need a higher accuracy in y direction than in x direction. And for this, I use a special kind of flat elements, and these elements are called layer elements. They are very flat, and they are tailored to be used for boundary layer flows. And in the end of the day, it means if you want to physically or realistically resolve what is happening in your boundary layer, you need to resolve the wall properly. And that's a big problem, because the change here is so high and the gradients is so high in the very near of the wall that you would need a really, really fine mesh to resolve this gradient here. It's the approximation of the curve is so large that you would need a lot of thin elements. And therefore, wall modeling was introduced, because if you would resolve this velocity profile properly for CFD models, it would result in very large simulations. And wall modeling is just about adapting the cell height of your elements in the near of your wall to the physics of your flow. And basically, wall modeling is just about a very fundamental relationship. And this relationship says that the dimensional velocity, so the velocity here as a dimensional velocity, so related to the inlet velocity, or to the relative velocity, is a function of the dimensional wall distance, which means I can basically describe this profile with a logarithmic function. And if we plot this relationship, and you can see this graph on the right side, on the x-axis we have, let's say, y plus, which is the dimensionless wall distance, and on the y-axis we have u plus, which is the dimensionless velocity. And please note that this is the logarithmic chart, so the axes are formatted in a logarithmic way, and you can see that basically for this whole viscous sublayer, this part here, let me mark it, everything which is happening here can be expressed by a logarithmic function. And this means, or basically the idea of wall modeling is that instead of spanning hundreds of cells in this viscous sublayer, we just put one single layer of elements there with a specific height, which is exactly that height. It responds to a y plus of 1. And then this whole viscous sublayer, instead of really calculating everything, we can model a velocity profile instead. And the only requirement we have is that depending on if we use a wall function or not, and which turbulence model we are using, so our y plus is 1 or between 30 and 300, depending on the turbulence model. Yes, and there are some other things. I don't want to talk too much about them, so let's make it very crisp. So two things we also need for every simulation. So the mesh is giving us a discretization, how we structure our problem. And then we need two things, initial condition and boundary condition. As the name says, initial conditions are used as the initial solution for our simulation. As you might remember from our last session, the way CFD simulations are solved, it's iteratively, which means we have a numerical approach, and it's like we are taking our equation, we're calculating it, and then the solution is the input for the next calculation step, which means we need initial conditions. And to make this a little bit more vivid, so for example, initial condition needs to be it needs to be similar enough with the solution we are looking for, but they don't need to be exactly the solution, otherwise we do not need CFD. So in practice, you usually, for example, if you do aerodynamics, you just initialize your simulation with a uniform pressure field and a uniform velocity field. And as better your initial conditions are, as more they are, let's say, in the same magnitude, like a later result, as fast your simulation will converge. And in contrast to that, boundary conditions are describing how our model is interacting with its environment. So if we do, for example, if we think about our wind comfort simulation from last week, the boundary conditions were, for example, the air inlet on the one side, the outlets, and the walls. We also have numerical settings. Since we're using numerical approaches to solve the equations, we also can change and adapt the settings of these algorithms. And usually, as a let's say less experienced user, you should not care so much about numerical settings and initial conditions, for example. Basically, the standard settings and default settings, which are on the SimScale platform, should be fine for most of the simulations. And there is one other thing I would like to talk with you about, which the so-called turbulence modeling, which is very important for wind comfort prediction, especially for wind load prediction. And Per will talk about it also during his presentation. Let me just quickly introduce to you the concept of turbulence models. You might heard about turbulence in the past, and there are a lot of different explanations what turbulence is, and in the end you can summarize all of them or simplify them to one thing. Turbulence is a chaotic change of field values in space and time. So what does it mean? If you usually, I think you already heard about transient and steady state flows. And from this point of view, steady state means that your flow field is constant at all the time. And transient means you have a changing flow field, which is most of the time also associated, for example, with changing boundary conditions. And turbulence is something very special. Even, let's say, if you have a steady state flow, and you would measure it in the real world, you will find out that even for a fixed point, your velocity and pressure are fluctuating a little bit all the time. And this chaotic change can be quite important. On this chart on the left side, you can see right now a velocity of a probe of a CFD simulation plotted against the physical time. And in reality, there is no steady state. All the flows are transient, and all the flows are more or less turbulent. And the problem with turbulence is that if you think about it, if I want to do a steady state simulation, I need to somehow average this. And the basic problem is, so what can I do? One option would be to completely resolve this turbulent profile, but these fluctuations are very small. So what can I do instead? I can only consider the average value. So that's what I want to do at the very first step. So instead of taking a place at velocity, at the flow, instead of taking a look only at the standard velocity, we will divide the velocity first into two components. One component is this red U dash, and U dash is basically our average velocity. And on this average velocity, we have the fluctuation, which is added on top of this. And now the idea is that we can calculate two things. We will calculate a mean velocity and additionally a field for the oscillations. The problem with this oscillation is that they are occurring on really different time and length scales, and sometimes we have like oscillation which have let's say are happening in 1,000th of a second, and on the other time you also can have very large scales. And there are two possibilities. One option is to really calculate or solve all the scales, which we would call DNS, which means we would really resolve all these turbulence fluctuations completely. And this dynamic numerical simulations are not practicable. And even the fastest computers in the world would need years to calculate a DNS simulation just of the flow around a single building. We are talking here really about one of the most complex things you can do with computers. So this is not an option for us. But there's another option. And this is where turbulence modeling is introduced. Because in most of the cases, it's not possible or practicable to directly calculate the turbulence, we will use a model and replace the oscillations. So, and instead having oscillations, we will introduce something else, because we cannot just take away something on one side of an equation. We have to do it on both sides. And so on the one hand, we will only consider the velocity to be made out of one component, the average velocity, and all these fluctuations are considered in the momentum equation by introducing artificial turbulence. So viscosity is the physical transport property in fluid flows. And now we will replace the physical velocity, which is the viscosity of the actual fluid, by a new viscosity, which we call the effective viscosity. And there we are summarizing physical velocity plus turbulence viscosity. And this turbulence viscosity is the artificial viscosity, which is not physically existing and calculated by the so-called turbulence model. And now we are able to calculate and simplify turbulence based on additional transport properties instead of solving all the time and length guides. And it is very important to understand that this is a major simplification. So it's not valid in general, and there is a kind of midway which is called LES, large eddy simulation, where those parts of the simulation which are really fine structures or have fine scales are solved using a turbulence model, and larger scales are solved with DNS. And yes, as I mentioned, when it comes to using a turbulence model, we recommend to use the so-called chi-omega SST model, which is a two-equation turbulence model, which basically combines two different turbulence models, one for this what is happening in the far field of the flow, and one what is happening in the near of the beloved body. And basically the turbulence model is made of two additional quantities which we will introduce. One is omega, which is a specific dissipation rate in the near of the wall. So omega is describing how quickly these eddies and vortexes are dissipated into smaller vortex cascades and structures. And epsilon is our turbulent dissipation rate, which gives us, let's say, the turbulent dissipation. So this cascade effects in the near of the or in the free stream. All right, and that was my fundamental part about CFD. Thank you very much for listening. And I see we have some people who raised their hand. Is there any problem with the audio, guys? No, so everything seems like to work. Okay, great. And now it's a big pleasure for me to give the word to Per, who will again give us a very interesting presentation, introduce you to the concept of wind load calculation. And yes, Per, thank you very much. I will make you the presenter right now, and the stage is yours. Have fun.
Thank you. Yeah, I will accept it. Yeah. So can you see me?
We can see you and we can hear you.
Great. Well, I'm Per from Vind-Vind, and we have been doing wind engineering for some years now, and mainly working in Scandinavia. For the past few years, we have made a validation project together with DTU, where they have provided some wind tunnel data that we have been trying to replicate, because that is very important for doing wind load. Wind load is about security and safety, and if you don't do it right, people will die. basically. When you're building, making a standard building, you should always use Eurocode. Eurocode is the European standard for doing wind load. Otherwhere in the world, you will have some other codes for that. But in Europe, we have Eurocode. It's basically a collection of some it's bright guys' experience over the past many years, and they have found out that where will things break, and from that they define some zones, and then you need to have the correct dimensioning in these zones. It is it's a thing for constructional engineering, and you should let them do that. If you want to do wind load on from CFD, you need to do it on the same level as professional wind tunnels, and that means that you need to make the same data as the wind tunnel does, and that is 5 hours of simulated time. Depending on how big your building is, it will take days, weeks, or months, and you have to do it for all the directions that are relevant. If you have a cube, you have symmetry, so you don't need to turn it around 4 times, so you can divide it by 4. It is quite demanding to do that, and well, the complication comes from that you don't have aerodynamic buildings usually. You have sharp edges, and they generate a lot of turbulence, and you don't have an inlet that is the same as when you're building a car. Then you have basically a free flow that the car is moving into. Here you have the turbulence from the surrounding buildings, and these eddies are very important for the load. Here we have the cuts at the center of a cube from a wind tunnel, with some smoke to visualize the eddies, and you see you have some dancing eddies here, and then you have some smaller eddies here that grows larger, and then you have some rather chaotic turbulence on the back. We have been doing this experiment in CFD, and when you have a uniform inlet, you have very stable eddies in front, and these are changed as you increase the turbulence inlet of the turbulence of the inlet. And what you are interested in finding when you're doing wind load are these extreme values, and they will not occur when you have a uniform inlet. You need the turbulence, fully developed turbulence in the inlet to find these extreme values that you need to have for dimensioning your building. So that is a big project to do that. But if you want to get started on making optimized buildings, you can, of course, do it without doing the full thing. And if you use RANT, models, which is the easiest models that Milad explained before, where you don't model the turbulence. There you can have the mean pressure around your structure, and that will give you a good indication of how changes in your shapes affects your wind load, and that would be the first step in optimizing a building. So there you can see if you have a thin high structure or a bulk low structure, and you can see the difference, the changes in the load. You will not get any facade effects from edges, rounded corners, or stuff like that. For that, you need to use LES turbulence models, and they give you a lot of the behavior around the corners. Remember, you still don't get the fluctuation from the atmospheric eddies that is important for getting the actual wind load, but you can optimize corners, rounding, see if rounded corners reduce your load, and you can see if you introduce some roughness on your facade, then you can reduce the eddy development. You can have some kind of spoilers that directs the eddies in some direction, and that is doable, and it is quite more computationally demanding than the advanced models, but you can definitely do that. If you are interested in high rises, then you need to have the atmospheric boundary layer, because the overturning moment is of importance for the high rises. And the wind speed changes quite a lot with height, and in Eurocode you have a concept called terrain category, where 0 is water, and terrain category 4 is full urban environment. So as I mentioned last time, when you're doing wind CFD, then you have model demands that are much different from doing architectural presentations. You need to have solid models, and often when you get a model from the architects, then they are not of the quality you need for doing CFD. And I will just refer that to the last demonstration that there we went through how to drape a shape and make mesh repair for making it ready for CFD. The qualities of the meshes are preferable having a closed mesh, but the SimScale platform can use open meshes as long as you don't have exposed holes in your surface. If you have holes, then they need to be hidden from your computational domain. So, to you, Milad.
All right, Per, thank you very much for this presentation. And regarding the last point you said, it's absolutely right. We suggest and recommend to use solid models, but in theory you can also use models which are not non-solid as long as, let's say, the diameter of your biggest hole is smaller than the smaller cell size you want to use. And in practice, that means most of the time that you just need to make sure your model is looking watertight and has no big holes. All right, so now let's do a short live demo. And like last week, now I would like to put you into the seat of a CFD engineer. And together we will take a look at ready-to-use wind load simulation and take a look also into the results. So let's start. Just 1 second, sorry. Wait, so what are we going to do today? Today we're going to take a look at a very well-known effect, which is called the crosswind response. And basically it's about, just imagine we're looking on top on this high-rise building. So this is a cross-section of the high-rise building. And the air is coming from the left side. So the free stream is coming from here. And then what will happen is, like Per mentioned, the flow will separate here at the edges of the facade, and we will have this vertex street, which you might also know as this Kalman vertex street, which is quite similar to that. And this transient eddies, they will create a resulting force which is orthogonal to the free stream. And the very, let's say, interesting thing about this crosswind response force is the fact that you get different loads for transient wind loads and for static wind loads. So this diagram is representing like the crosswind force as a function of the wind velocity. And if you have a transient wind load or transient flow, you will get a lot of amplifications for defined velocity ranges, which means that it can be necessary to optimize your building for both, and it's a trade-off in the end, because things which are helping to, let's say, reduce the transient wind load can increase static wind load and the other way around. And today we want to do such a wind load simulation on our own. So again, we will need to import, first of all, export the model as a closed model from Rhino or another CAD tool. Then we need to import it and mesh it. And once we meshed and defined, let's say, the local size of the elements, we just need to define the boundary conditions and set up the simulation, and then we can post-process and analyze the result. And again, I have prepared a project, and this is, by the way, a public project. So if you just go on our public project page and look for building vertex shedding, you will find this project and you will be able to copy it. So now let's open the project and take a look inside. Okay, so this is our geometry. It's very simple. I know it's just one simplified building geometry. And yeah, so when you import the geometry, you have, as you know from last time, we have different options. You can basically upload some CAD files like STEP, IGES, STL, and also upload native CAD formats from Rhino, Autodesk, and SolidWorks. And the first thing you can check or you should check is the size of your model to make sure that you don't have any problems related to the units. And since this question also came up several times, we also support English units. So you can choose if you want to go for meters or for inches. Right, and if you want to create a mesh, you just click on Create a New Mesh, choose the geometry, click on Save, and then you can choose which meshing algorithm you want to use. And since this is fluid flow, we recommend, and we have usually have more complex geometries, we recommend to use a hex dominant mesher, and you can use the automatic mesher where you for external flow, where you just have to define the total mesh fineness and the size of your control volume of your bounding box. So this would be much too small, and we can make it a little bit larger. Can adapt it and bring it to the right size, but we can also have full control over the meshing settings. Then we are defining this base mesh size, but also like refinement regions. And then if you take a look at the final mesh, you can see like that here we have this different refinement regions. We find the meshes in here of the surfaces and the edges. Right, and once we have set it up, your mesh, you just need to create a new simulation. Click on New, again choose Fluid Dynamics, Incompressible, and here, by the way, you can also access the example. Just click on Create, and then you have all the standard settings. By the way, for turbulence modeling, by standard, we have K omega SST. If you want to do LES, it's also not a problem. Here we have also 2 LES models. And then you basically just need to define the mesh you want to use, the material properties of the fluid. In our case, it's air. We will just import it from our material library and assign it to the whole fluid domain. And finally, you just need to define boundary conditions. So how is our model interacting with the environment? And the easiest setup we can do is to say this is an inlet with, for example, let's say 20 meters per second. This is an outlet, for example. And that's a simple setup we can do, and basically now we can run our simulation. Let me delete this again. For sure, we recommend some different setup when doing wind load analysis. And one thing which you should, for example, do if you want to use the atmospheric boundary layer instead of a fixed value, you just need to change this to a function, and then you can upload a CSV file which is representing your velocity profile, and you can export this velocity profile from some other tools or from some table books, and then instead of having a uniform inlet velocity on this inlet surface, you can have the same wind gradient like in reality. However, once your simulation is done, you can, for example, immediately take a look at the forces. And by the way, this was a transient simulation, not a steady state one, so this is like real time. And here you can see like how the forces are developing over time, and for sure you can also take a look at the 3D simulation results. They are loading right now, which can take some time when running webinar software in parallel. I'm sorry for that. Yes, in the meantime, maybe I can answer some questions.
Yeah. Okay, I'm back. My internet just fell out, so I had to reconnect.
All right, Per. I think it was good timing still, because at that moment I was taking over the presentation, and right now I just made the live demo about SimScale, and right now we're taking a look at the live results. Maybe something which is also interesting for you, Per, for this atmospheric boundary layer, I showed them that you can just upload the wind profile as a CSV file. And from our discussions, I know that a lot of other tools are providing these wind profiles, right? So you can just, for example, if you're based in Oslo, you can just export the the main wind direction and the wind profile, right?
Sorry, once again.
I just said that when it comes to using the atmospheric boundary layer, you can just upload on SimScale a CSV file with the wind profile and use it as the inlet boundary condition. And
I usually use a predefined atmospheric boundary layer from the in the open foam library.
All right, good to know that. And now I just wanted to show them like how you can, do, for example, a slice through the flow field. For example, you can change the direction, etc. All right, Per, we will talk again during the Q&A, right? So now let's proceed with the demo. And yes, here I just made, for example, a slice through the flow field. And as you know from last time, you can basically you have unlimited possibilities for post-processing. So you can take a look at whatever you're interested in. For example, this is a pressure distribution. But we can for sure also change this to velocity distribution or whatever we're interested in. We can create streamlines and a lot of more things. And just one thing, since it's a transient simulation, we have different time steps. So here you can see how the flow is developing and fluctuating. All right, so let's get back to our slides. And now take a little bit look at the results. So this was our case. We had this cross-section of 20 by 20 meters, a height of 150 meters, and one coming from X direction. And yes, let's first of all take a look also at this slide to understand why CFD is so valuable. Because if you think about it, once I have defined my simulation, I can basically test hundreds of different concepts. And I just need to update the geometry. And especially in building design, and at the very first beginning, in the concept phase, this is very, very helpful. And in our case, if we do some more post-processing, this is how the result look like for the initial design, the initial shape, and you can really see like this complex flow structures here, and also how they are induced, because they are generated by this wake region behind the building. And what we can see here right now is the animation of the velocity. Yes, and it's by the way, a periodic effect. And if you just think about it, this blue areas in the end representing our dead water zone, and this is moving all the time, which means that also our load will fluctuate over time. And the great thing is that yes, with the simulation, you can really, as I mentioned, test a lot of different concepts for high-rise design. And what we did, we based on that, on the first simulation I showed you, we created a second one just by copying the meshing project, changing the geometry, so it's exactly the same settings. The only difference is that in this case our geometry have rounded corners. And we just copied the simulation setup, and then we started to compare both designs. So, and here you can see the initial design, and below you can see the round corner case. And on the first view it looks exactly the same, but if you take a deeper look you will see that for example this deep blue areas are much smaller for the rounded case corner case than for the sharp corner case. And especially if you take a look at the width of the wake, it becomes obvious that having this round corners is reducing the flow separation here, and therefore also this whole wake structure becomes smaller in terms of width but as well as length. And here you can see the forces compared. So we had the same load case, and what's very interesting is that it's basically a completely different kind of physics. When we have this initial design with the sharp corners, so we have much stronger intermittent forces. But if we use rounded corners, the forces in total are weaker, but they are periodic. And I hope that this showed you like which high bandwidth existing during the conceptualization phase of building design, and that CFD can really help you to understand fundamental differences in your facade design and how this will result in wind load. And this was just a very simple example, and there are a lot of other ways to use CFD and wind load prediction for building design. As I mentioned at the beginning, it's really helpful for optimizing the building shape and orientation, and mainly to improve the interaction with the surrounding, which is quite similar to wind comfort. But at later stages, when you have, for example, your rough shape, simulation still can be used, especially CFD to improve your design. So especially at, let's say, when you start to define the details, and if you want to use complex facet structures, you need some loads, and there you can use CFD to optimize, let's say, the load on the facet, to optimize small structures, and use it then as an input, for example, for calculating the structural analysis. Right, and that's a final aspect I would like to talk about, which is validation, because a lot of people ask us, well, that sounds really nice, but how accurate is SimScale compared with other tools if it just costs a fraction of on-premise solutions? And therefore, we provide a so-called validation database, which you can find on the SimScale website, and where you will find a lot of different real-world examples where we validated our simulation tool against physical experiments. And this case, for example, this is a benchmark case from a university in Japan, and they basically just compared wind tunnel measurements of this geometry with CFD results. And the blue line on this chart is representing, let's say, the experimental result, while the red line is representing the CFD result. And so we did the simulation, and we measured 3 profiles and positions A, B, and C. And you can see that for sure there is a slightly difference, because on the one hand we have an experiment, on the other hand a virtual or a numerical simulation. But however, the total trend and also the total representation is really, really good. Yes, and basically that's everything from our side. Thank you very much for joining us again. And yes, like last week, tomorrow we will send you a link to the recording and also to some useful resources. And now we have time for the Q&A. So let's see what questions do you have. And right, so Felix Persson asked me if I can show how to set up the force plot, for sure. And just in general, we decided not to really do a step-by-step demo during this webinar, since from our experience, people like it more to do it on their own. Therefore, I might skip some steps. But for example, setting up the force plot is quite easy. Okay, I have to log in again now. You basically just go to your simulation, go on result control, and then you can add a new force moment result control item, and then you just need to define which faces and patches should be included in this calculation. For example, in this case, I will just take the whole building. Then you can apply center of rotation if you want to calculate moments too. And that's it. All right, it seems like most of the questions were already answered on the fly in the chat. If there are no questions anymore, I would like again to thank you very much for joining today. And I would like also to thank Per for his 2 great and outstanding presentations. And yes, I would be really nice if you also joined for our last session next week, which will focus on internal flows and how to use CFD to optimize HVAC and ventilation in building projects. Next week, my colleague David will guide you through the webinar. Yes, thank you very much. Hope to see you next week. Have a nice weekend. Bye.